Okay, Ewan, following last week, we finished up saying, well, the important thing is cyanobacteria. If you're a really good farmer, you're farming cyanobacteria to make the whole farm work.
Absolutely. It's the basis of all life. It was what started the planet. It took it from a acidic, anaerobic environment into what we can live in.
Well, we've put this together so that people can understand that better. So let's rip into that one then.
Yeah. We just need to take it nice and slowly and try and remember all the little bits and pieces as we go. But they're incredible. They oxygenate the planet. They consume carbon, deposit the carbon to create food. They're the bottom of the food chain. As I've said before in the DNA video that we did, if you want to go back and look at that, they're incredible that they can restrand their DNA back to the original source.
Right.
So if there's any defects or whatever, they restrand it back to the right place.
That's incredible. That must have significant health benefits too.
Absolutely, because every part, as science has discovered, and that when it's consumed, it goes to the next level. So the DNA and the nutrition goes up the ladder. And we'll see that as we go. As you see the starting point, it's quite incredible how microscopically small this pasture-eating monsters come along and go...
Yeah, exactly. Yeah, true. So cyanobacteria, the microbes that change the planet, that's a bold statement, isn't it? The microbes that changed a planet.
Well, I didn't make the statement. I just sort of read it and I go, yeah, absolutely. So these forms of organisms, they're photosynthesizing bacteria. Okay, so they can take the energy from the sun and turn it to a different energetic form. So when they took the energy from the sun, then they took the CO2 from the atmosphere and converted it to carbon organisms and released oxygen.
Right.
So we can breathe.
Yeah.
So there was no way that we could have lived in the environment before these guys come along.
Okay. But the way that links back to farming is that we're able to improve the lot of cyanobacteria out in the field and then improve the lot of the farmer.
Absolutely. So what we have is that these guys have a nutritional profile that they love. And when you can grow these guys, you can grow just about anything after that.
Right.
Because once you've got these guys working for you, they go, okay, you've got all the minerals for genetic sequence. We've got the tissue salts to put this into water. You've got the cofactors that can actually take ammonia and turn it into amines. You can take the urease enzyme, for example, which is part of this whole process where you need a little bit of nickel and it converts nitrate to ammonia. So there's a whole lot of forms going on in what everyone thinks is cyanobacteria only live in the water, but they don't. They live in the soil as well. They do need water to proliferate, but they're environmentally hardy as hell. Live in the South Pole, live in the deserts, live out on your farm. They don't like chemicals.
Yeah, it's a common misconception, isn't it, that they only live in the water? I mean, sure. I mean, they're everywhere, in sea spray even, but on the farm, it's an unusual sort of concept to think that they've made it out to the farm. But I guess everything at one point was underwater, so.
Yeah, well, the evidence is plain. I mean, it's well documented that they live in the farm. I think the part that you've got to come to grips with is that when we're actually looking at the growth in the carbon, and we'll see in the video today, or parts of what day, our last test showed that we grew 10 tons of carbon per hectare in the 150 to 300 mil profile last year on the bottom part of the farm.
Yeah.
Which then equates to it's about 20 tons of dry matter you grew, which is phenomenal. That's above the ground.
Yeah.
But the cows ate it and took it away, and they left the shit in bits and pieces. So where did the rest of the weight come from? So it came out of these guys, and people are not recognizing that they are the best cover crop or the best regenerative of our soils. They have not identified that these guys are the most prolific. They will do the biggest job, but they need nurturing.
So they're the regenerating motor, the big regenerator.
Yeah.
That doesn't like aluminium, if I've learned anything from you, and doesn't like chemicals.
That's right. They're the big kahuna, but you can't even see them. And so we've got some examples as we move on through this process just to see what the accumulation is like from how prolific they are.
Okay, well, let's have a look. The first one here reminds us a little bit of what we saw last week, because we've got that slide from the increase on the land of carbon.
That's right.
Right. but we're drawing that correlation with the cyanobacteria.
Yeah, well, see, from the one we did last week, when I said to you, if we increase the soil carbon by 1% in a certain in an area of 1 hectare within 150 mil depth, well, these are the figures that you get.
Mm.
Well, I got the soil test back a couple of days after we did the video.
Yeah.
And that's exactly what I'd done.
Is that right? And you got it back just within a couple of days of it?
After he came back. So, yeah. And it wasn't in the top 150 this year.
Okay.
It did it in the bottom 150. The top one stayed. And so I'm seeing these changes in the minerals status and how it's going on and how my soils are getting deeper and how much more grass we're growing.
Mm.
Now, when you look at this nitrogen-fixing cyanobacteria, look at the array of them. There's millions of the damn things. I mean, there's unbelievable quantities of them.
Yeah.
But if you're going to produce nitrogen, you're going to come out of the atmosphere and you're going to photosynthesize, then you've got carbon. You cannot have no carbon. So this is what's happened. We've increased the carbon. Oh, we've put all the nitrogen in the soil. The phosphorus has become available. Sulfur has become available. So now my soil depth is growing. And we've seen a very reflective amount of growth above the ground is relative to what we get going on below the ground.
Okay, and for people who are fixated on nitrogen, then you're growing your nitrogen at the same time.
I've got a nitrogen factory.
Yeah. It's kind of not the point, but for a starting sort of entry point to go, okay, maybe this is something to look at, and you're really buying nitrogen all the time, then this is like, all right.
Yeah, instead of going to Caponi and buying gas to make nitrogen, I've just sorted out the environment for the cyanobacteria to produce it ourselves.
Yeah.
And so hence we've got the carbon, water holding capacity, available nitrogen, and in the summer what happens is the sun beats down and there's a bit of oxidation in the carbon. So there's nitrogen, phosphorus, sulfur released. And then in the wintertime when it cools off and the grass doesn't grow so much, the cyanobacteria go bonkers because they're not so fixated with temperature. They're actually more about energy from that sunlight. They're actually much more efficient at photosynthesis than pasture species are and higher plants.
Really?
Way more efficient. So we know that if we can actually create the right environment in the wintertime, they'll regenerate. And they love that moisture. Like say, and that's when we see the big growth in the winter because the temperature is lower, but there is moisture and they can go, yippee, let's go.
Yeah. Okay, well, this is an interesting one. This is calcium forming as limestone, but it's the accumulation of cyanobacteria's activity.
Yeah, so this is one that a particular form that has a lot of calcium in its structure. Okay, but it's calcium carbonate. Okay, well, it's what lime was stated.
Right.
Okay, so it's bringing the calcium in and it's bringing the carbon in. Okay, and the idea is that in the ocean, in certain environments where the ocean currents come and the right nutrient flow comes, these tiny microorganisms, each individual grows a skeletal form of calcium carbonate, dies, falls to the bottom of the ocean. And we've all seen how big lime quarries are and how massive they are. Well, they all started off, the majority of them started off with little wee, tiny little microbes. And so these stacked on top. And so this is the same with sea-based diatoms.
Okay.
So that they're in that form. They are a silica-based framework. Yeah. So the same thing, massive deposits.
Is this actually, when you look at them up close there, is that actually, are we looking at cyanobacteria, each of those little circles?
You'd have to go back and look at all the information that we were looking at. But what it's doing is it's really blowing up to try and give you an idea of all the organisms that were involved in it.
Because that's a close-up on it, isn't it?
Yes, very close up, yeah.
But, well, actually, I mean, the background shot there that we chose to put behind that is a quarry. And lime is something that people consider quite important. So, hey, look, here's another connection to the very important cyanobacteria.
Absolutely. And this is part of what we're seeing in the soils is that when we feed them correctly or give the right environment, the biology that takes over and the interaction with the plants and what grows is quite phenomenal for what your own requirements are. There's a signaling event going on up and down the plants and what the biology is and that. And so nature's far smarter than we are. You know, we've got all this electronic stuff and internet. They've got microscopic and electronic signaling and all sorts of stuff. So, like, I mean, do you think that we've reinvented something that's been going on a few million years?
No.
No.
Nothing new under the sun, as they say.
No, nothing new under the sun. It's just a slightly different concept.
Yeah.
So this is how prolific they can be.
Mm-hmm.
And so, people haven't seen how prolific they are because they're not talking about them.
Well, let's go to the digestion process. I enjoyed making this one in ChatGPT.
Yeah, it was.
So
cool.
that's a tardigrade, or what you might call a water bear eating a cyanobacteria.
Yeah, it's a funny little thing. But we will see in the next video where they actually, but the cyanobacteria.
That's probably size accurate too, by the way.
Yeah, 1,000, 1,000,000 times up. Yeah.
Yeah.
But when you look at the cyanobacteria, each one of those strands that it's eating, that's a single cell.
Yeah.
And then it's replicated itself to another single cell, another single cell, another single cell. So we got just a single cell organism joined with another single cell, and it just goes on and on and on and on. So it's just a replication plant. And they are, as I say, they're photosynthesizing bacteria. So the closest thing to a plant and a living system. It's quite an interesting process, really. It's like, what? It's an animal? But it's got organs inside of it, but it's not a plant.
These green strands of cyanobacteria that look almost like, because they're found in the ocean, they look like as though they could be strands of weed, are actually a sort of a strange hybrid of bacteria and plant.
Yeah, well, all seaweeds and all these are all these same sort of forms.
Really?
Yeah, and so we've neglected where we came from, okay? And so the problem that we get is that when I talk about cyanobacteria, the first thing it's toxic, it's dangerous. And
yeah, because they've got an algae bloom reputation, right?
That's right. And they come from environmental fixate, like when there's too much nitrate and not enough oxygen, the particular ones that turn up in that environment create these toxins. And I know if dogs drink that, it's it'll kill them. It's very dangerous. But do a little bit of homework to realize how many species there are of cyanobacteria. There's bazillions. And, as we've been going through this sort of thing, it's like, oh my God, what are we going to put in? What can we show? And it's trying to make it interesting. God, it's a single cell organism. God, it doesn't go out on a party or anything else like that, but it just keeps photosynthesizing,
It doesn't go out and party. It's got a lot of friends, I noticed, in the images of the cyanobacteria family.
Yes, and lots of things want to eat them too.
Yeah, like these water bears. Let's look at the next one. Good. And speaking of things that actually want to eat them, should we play this?
Yeah,
that water bear, that tardigrade image from ChatGPT. I mean, it's close because check this out. This is actually a real one that is eating cyanobacteria. It's so microscopically zoomed in that actually that little creature is virtually transparent.
Yeah, so just play it again. I mean, look at the way that this is going about. Does that look anything like a sheep grazing or a cattle beast grazing? It's just consuming cyanobacteria, the strands of them, and digesting them and putting them into the ground. Now, can you imagine how productive that is? If I can put 10 tons of carbon into the soil in 1 year, how productive these little gobblers are eating all the cyanobacteria. Now, we see this with the worms. In the wintertime, they go down and they eat, they'll be eating the tardigrade and the cyanobacteria, and then they bring the worm castings back up and they set them on the top of the soil.
Right.
And so they're bringing the fertility back up. They're recycling the whole process.
Yeah.
So it's an amazing thing. It's like we're living in a soil ocean and we have to treat it that way. We have to treat it nicely. We have to put the right products in, the ones that are missing. And we're seeing this. And when we do a herbage test now, when we come back and we've just got some of them back, and you can just say, oh, look, our our calcium's gone up, this has gone up. Oh, our cobalt's starting to slide a little bit. And this is an indication of how much soil we grow, and then we can go, okay, there's the targeting figures. We still need a bit more boron. Let's look at our soil tests as well, and we can start to isolate, okay, those are the 3 things that we need to identify that we have to deal with this year if we want to keep growing soil, because that reflection of soil and growth in the field is phenomenal.
Okay.
Yeah. I mean, at the moment, the farm just is phenomenal.
I mean, if you can't see that interconnection from the microscopic to the macro, it's kind of lost, isn't it?
It's totally lost. And as we go on, like we revert back to some of the videos that we worked on in the carbon thing about showing how destructive we can be when we destroy these guys' homes.
Yeah, yeah. Well, that takes us to the single cell and what makes it up, because that long strand of cyanobacteria is made up of many of these.
Absolutely. Well, that is just one. Yeah. So it's each one of these is a single
Because they're
cell.
all joined together.
Yeah.
Yeah.
And so there's all these fancy big word names and cell walls, but basically there's 12 individual tissue salts required to actually create a cell. Then you've got all the cofactors like iodine, nickel, cobalt, copper, and all of these are really important in their production. And then we see the nucleoid in the middle, a DNA ring right in the middle, which actually is that reproductive process. Now, the reason that...
No, so what's referred to when you say that cyanobacteria is capable of restringing its DNA, that's what's being restrung in there?
Right. It's going back to its perfected form.
Wow.
And so this is why everyone sort of looked at it in the ocean before, because the ocean has all of the minerals and subatomic particles to grow a healthy DNA strand. It's also got soluble silicas. It's got all the minerals and everything else that you need to actually do this. So this is why we always seem to go back to the ocean to look at cyanobacteria production, or how we've looked at it in the past. We think it's just in the ocean. And then in the fresh water, we see it when it goes wrong with these nasty poisonous ones, when things aren't right. And there's a whole range of reasons for that. Silicon is one of the biggies in this. Is cellular structure really, really required in the environment here. So if they don't have that, they don't actually proliferate. So that's one of the things that we're really showing, is that you need the silicon, you need the iodine, you need the nickels, you need the cobalts, you need all of these things in a particular order to get these guys to go.
Okay.
And when they go, hold on.
Yeah.
Yeah. So this is the tissue salts, and I'm going to do a podcast on these individually because it's a big subject, huge subject.
Yeah, this is interesting for me, like looking at these, because I've come across these in the past from, I guess, an alternative health perspective, because I've seen these being sold in pharmacies for your good health, and you're actually talking about them in relation to the health of a farm and the human body as well, right?
Everything, yes. So one of the things that's really not discussed in agriculture, there's lots of things not discussed. Look, phosphorus, right?
Yeah.
Okay, it's an anion. It's a negative charge.
Mm-hmm.
So it's going into a plant which has a negative charge.
Okay.
How does it do that?
You're asking the wrong man.
Yeah, I know. But it's positive, negative charges, right?
Yep.
Negative doesn't get attracted to negative.
No.
Okay, but positive will flow to negative if there is a, right. So you go through photosynthesis, you bring the carbon in from the atmosphere, you bring a negative charge in the plant, and there's an electrical charge in the soil, and it wants to go there. So that's just the way it goes.
Right.
So when you change these anions into salts, they become a positive charge, and they are movable by the electrical current.
Okay.
So if you look at NatPhos, that's sodium phosphate, MagPhos, magnesium phosphate, ferrum phosphate, calcium phosphate. So there's 5 forms of phosphorus that go into the plant to make a cellular structure up. Every one of them has an incredible function. Ferrum phosphate, it carries the oxygen. Magnesium phosphate, that's the expansion. NatPhos, that's the pH stabilizer. Calcium phos, it's the bone structure. Kaliphos, it's the spark. It's the electrical sparker. So what we're looking at is, if we want to grow healthy animals from the soil up, we've got to realize that they need to be, or they should be, in these mineral salts themselves. So if they've gone through a digestion in the soil through the cyanobacteria, then we got these little munchers come along. They come along and gobble that. Then they lay that down as humus. Okay, and the worms come along and gobble them up and redigest.
Is that what the tardigrades do?
Well, the tardigrades are going to poop, aren't they?
Sure.
Yeah.
So it becomes humus. That's interesting.
Yeah. So so the tardigrade gets eaten by the worm and all these other microbes in the soil. So everything gets digested and turned into humus.
Yeah.
Okay. So then we turn that humus in the oxidation of carbon and the release of nutrients is all these salts will be released as they're required.
Right.
Now, it's not just soluble phosphate. It's now ferrumphos, magphos, natphos, and they've all got a job. So, natphos is a real indicator. I mean, it's crazy how these have been all lined up with the zodiac signs and their requirement. Libra, it's the scales of justice, right?
Yeah, that's kind of fascinating.
Yeah, but
Yeah,
natphos,
interesting.
it's the pH balancer in the body. If you've got acid guts and you keep taking, calcium products, forget it. Go and take some natphos. It doesn't take long. Your pH will balance in no time. Okay, and so there's all these things that are, part of the process. You're getting cramps, you get magphos, it releases the muscles again. So these are really important, and it's important to get them in these forms that then we want to go and grow pasture and then really healthy animals, because the animals can take this stuff up as well.
True. I just want to add the reason that looks like it's come out of a book is it's actually come out of Ewan's book.
Yeah.
You should probably do a plug for your own book.
Oh, yeah, you should read my book.
Well, you might need to tell them the title.
It's all right. It's at the end.
Okay. Fine. All right, let's hit the next one.
So this is, I guess, the thing that I'm trying to get through to people.
Yeah, Google it.
Google it. And it's like,
this information is out there.
It's everywhere. But look at it. Cyanobacteria perform oxygenated photosynthesis, a process that releases oxygen by using sunlight to convert carbon dioxide and water into energy. Hey presto, we produce sugars, energy, whatever from the sunlight. So you don't want to waste the energy that comes by. So the sun comes up every day and you can use it for these guys. Now in the winter, this is when they go nuts. This is when we grow cyanobacteria till it goes out the gate. It's just, you just see it when it goes off. You end up with 15 mils to 20 mils of worm castings over the whole farm.
It still boggles my mind that it happens in winter.
Yeah. It's brilliant.
Yeah.
It's gobsmackingly brilliant because...
I mean, winter with still enough warmth, like certainly in New Zealand winter.
Oh, yeah. Well, I don't know when that stops in the colder.
Like how much is too much?
How much is too much? But, like in this country, to the bottom of the South Island, it's fine. It's great. You go for it. So this gives you the opportunity to reload for spring.
Yeah. So spring is doing what spring's meant to do.
Absolutely.
Yeah.
You've got it locked and loaded, ready to go.
Okay. Now, this takes us back to last week and reference and credit to Dr. Louis Schipper. This is taken from his YouTube. We talked about his YouTube presentation that was a Grasslands conference last week. And we're just referencing it one more time because this highlights and makes the point about what's happening with the cyanobacteria, right?
Yes. And this is the thing that these guys haven't been credited for what? The soil carbon grain.
Cyanobacteria hasn't been credited.
No, they haven't been credited. And they haven't looked at this right down to the inty-bitty, what are the limiting factors that stop this? No, one of the massive limiting factors, which I've said, is that the lack of silicon. They need silicon to, soluble silicon as silicic acid to explode, right?
Mm-hmm.
So we get into that part. Then you've got to look at all these other trace elements that go with it. But they can't stand sprays. They just, herbicides. They'll just nail it, kill it, wipe it out completely, absolutely destroy it. And they can't stand aluminium either.
Right.
Same thing. It's like any bacteria exposed to aluminium, it will die. That's why they make antiperspirants with aluminium.
Yeah.
To kill the biology. So when we look at the evidence of what we're showing, is what Louis Schipper was saying is that after 1 year cropping, the carbon block dropped 8 tonne. It did it again. And then once it went back in grass, it didn't recover. Now, what I'm trying to point out is that the issue about the spray, when you spray it and kill it out, the first year it's fine. You get a pretty good crop because what it does is the carbon that is there then oxidizes. So it gives your plant carbon dioxide to photosynthesize with, and the minerals get released from that carbon that's in the soil. And hey presto, you get a crop. So you put the spray on and you grow a really crop. You go, I'm really good. And then in this case, they've done it again. But now it's not recovering. It won't, right? So the residual effect of those chemicals on that process is gone, stuff you. So the first observation is that there's nothing wrong with the chemical.
The chemical.
Yeah, the first observation is that you sprayed
of course, because the first observation is the chemicals helped.
Yes.
Right? Because look, the very first uptick in following that spray on is everything's cool.
Absolutely.
Yeah, I'm with you now.
And so this is the problem we got, is that people are saying, well, I sprayed it out and I put it in, it's all good, it's great. And I did it again, got not a bad crop, put it back in grass and it just won't do. There's something wrong with the grass species or something else wrong with this or something. And it's a cumulative effect that's gone kaboom, you're in trouble. And so,
according to this graph, you're looking at a year later, you see the first sort of lack of production turn up. And then 2 years later, it's just really, really low.
Yes, and then it won't come back. And this is...
So I guess the lesson there is you can't assume just because straight after a spray, that short-term quick fix is actually not having a long-term bad effect.
That's exactly right. That is exactly right. And this is when this was presented. Louis Shepherd says, well, we don't really know why it didn't come back, but, it did, and perhaps we can find out how we might get it back or what sort of plants we need to put in. It certainly, there's a huge part to play with plants, multi-species passes. They put down sugars. They call it the liquid carbon pathway. There's an exchange of energy and minerals are given up. But I can grow way more carbon in soil with cyanobacteria than thinking that you're going to do it through other higher species of plants.
Mm-hmm.
It doesn't work. I haven't seen anyone else be able to get these sorts of numbers. Yeah, and we're being as accurate as you can with doing GPS coordinates back to the same place, same process every year around the same time.
Yeah.
So we're trying to be as accurate as you possibly can. So if we go on to the next slide, this here, the red lines were pastoral mule paddocks. So this is the usual process: spray out the paddock, put new pasture in, and they wouldn't recover back to the normal.
And I'll just credit this Louis Shippers again from that same conference where he presented this information and we're just commenting on it.
Yeah. Absolutely.
So, and it's great information.
It is great. I mean, I haven't got the time to do this, but it's just showing you, look, when we did pasture renewal, it didn't work. And I hear this from people. They go, oh, well, I put all these regenerative species in and it didn't work. And there's a lot of people using the regenerative process and they spray out the paddock and then they put a multi-species in thinking it's going to come right.
Right.
And you're going to go there. You're going to spend a lot of money on the species and you're going to then not have a very good result. And like if you see what's going on the farm at home now and how much carbon we've grown and the species we got, we don't have to introduce any more species. They're there. They change with the soil. And they're brilliant. They go change throughout the season. They fit the seasonal qualities that we need.
All right. So just, if you wouldn't mind summarizing the 3 lines and what's happening there one more time for me. Just so
basically, and this is a really interesting. See how it goes right down in the bottom of the winter, okay?
Yeah.
And that's the worst possible time for the sprayed out regen paddock?
Yeah.
Well, that's when it should be at the top or should be up, climbing and actually getting up and over, ready for springtime. And so instead, the cyanobacteria have been wiped out. So when you were expecting for now that I've informed everybody, but where I would be expecting that big growth to be taking place.
Where the reload should happen for spring.
Yeah, it's gone.
Yeah.
It is absolutely gone. The paddock's buggered. The grass isn't growing on top. Nothing's happening underneath.
Right.
And so you've
destroyed that cyanobacteria motor. That's
right. And you've killed the fungal species off as well. So, that's something that we got to, really take into account. The fungal species clean up the environment. The cyanobacteria are productive in it.
Yeah. Yeah. Completely makes sense.
We want to see these. We want to see these red lines. I'd like to see them above the black there.
Yeah.
And then going to the average in the season where it was actually doing its job.
Mm-hmm.
But in the meantime, you might, over 3 or 4 years, you might gain 20 tons of carbon in the soil, get down to, 300-400 mils of depth of soil, grow a lot more pasture or whatever you're trying to grow. And you can do that quite comfortably.
Yeah. And in that way, recover minerals that you were otherwise paying to put more on from a bag.
Absolutely. Because that's one thing those cyanobacteria are marvelous about. They're great at harvesting those locked up minerals and bringing them into an available form. They're brilliant.
Yeah. Okay, let's have a look at the obvious, but, it's kind of cool. This is where they live, right?
Absolutely. So you see this one over in the desert, like there's plants there, but they're looking pretty down and bedraggled and horrible. And you look at the soil, there's no carbon there. It's all been burnt out, right?
Mm.
But in this environment, because we haven't touched it with chemicals and all that, but in this environment, when it rains, you see the desert blooms.
Yeah, it comes to life fast.
Real fast, eh?
Yeah.
Yeah, well, it's the cyanobacteria that are actually doing that first. They actually go through a life cycle and give up the nitrogen for the plant to grow.
Right.
And so it's so fast, they just explode into action. So here they are living in soils that get up to 50 to 60 degrees. It rains.
Boom.
Let's go, boys. And next thing, flowers come up. It's fantastic.
Yeah.
Goes dry again, dies off.
Yeah.
So there's a great example of that needs moisture. Now, you look at the icebergs. Well, that's another perfect example. It can't do anything while it's frozen solid. As soon as it defrosts in the spring, we get this massive cyanobacteria explosion around the poles. The krill eat that, then the herrings eat that, then we get this huge following on effect. It's bleeding freezing.
Yeah, yeah.
It's absolutely freezing. But it's relying on photosynthesis, electromagnetic energy around the poles. Let's go bonkers, okay?
Yeah.
And so when we look at the farm going, oh, it's a much nicer environment to live in here than the dry of there or the freezing there. But we have the same explosion. We have it in the wintertime.
Yeah, you still get those seasonal shifts.
Absolutely, yeah. So let's get them back.
Yeah.
And like some of the things that we're seeing from this, I mean, we've got some herbage tests that we've got to go through in other videos, but I got one just back. Oh, no, I got several back this last few weeks, which is really showing that we've taken where silicon was, say, 20 or 30 parts per million, and aluminium might be 200 parts per million. And there's weeds and shit everywhere.
Mm-hmm.
Now we've got the aluminium down 30s and 40s, and we got the silicon up to 150, and we can actually see the corresponding crossover that when the thistles disappear. It's like you can actually see, you won't have any thistles now, or they'll be just about gone. And it's like, yeah, that's right. Aluminium's gone, silicon's up. Now, they're a huge part to play in this process because they break down that hydrated silica into silicic acid, which is then available, and hey presto, we can have a whole lot better functioning farms.
And as always, the answer is fix your soils.
That's right. There it is. And it's home. And there's the book, An Eco-Farmer's Discovery.
Oh, I knew it was there somewhere. No, now, if I'm not mistaken, so that was from page 71 or something, that what we were looking at earlier with the tissue salts.
Yeah.
So that's in that book.
That's absolutely in there.
Okay, great.
Yeah.
Cool. Well, thanks for another one. I'm glad we finally got to cyanobacteria. We'll probably talk about cyanobacteria again in the future because it's so critically important. But as always, I would encourage people to go back to the soil test video. It's perennial. It's evergreen.
Yes.
And also a thank you to the people that have subscribed. We hit our 1,000 subscriber mark a couple of weeks ago, and it's been awesome, actually, to see the uptick and the views and the people and the great comments. If you've got any thoughts on this, please hit us up with them. We're there to answer them.
Yeah. Put your questions in if you've got,
Yeah.
And we'll either direct you to a video we've done already, or we'll have to do another one on that one.
Yeah, I say we're there to answer them. I don't answer them. Yeah. Ewan answers them.
Cool.
Keen to dive deeper? Check out our audiobook, An Eco-Farmer's Discovery, on Spotify, or grab our free ebook, The 6 Things You Need to Improve Soil and Farm Profit. Links in the description.